Hello everyone. Today I'm excited to share my thoughts on migrating monolithic SaaS to serverless, achieving scalability, cost reduction, and development agility on AWS. Hi, I'm Srikar Kompella, a senior software engineer with over 13 years of experience. I've dedicated my career to crafting innovative and scalable software solutions. If you have any questions about this presentation or anything related to migrating monolithic to SaaS in general, please reach out to me at reachsrikarkompella@gmail.com. So let's start. Why choose Golang for serverless architecture? Golang's strengths align exceptionally well with the demands of serverless computing. High performance, Golang compile nature results in rapid execution speeds and minimal latency. Crucial in serverless environments where costs are directly tied to the execution time, benchmarking consistently shows Golang functions outperforming interpreted languages like Python in AWS Lambda scenarios, often exhibiting significantly lower latency. This translates to reduced execution duration and consequently lower cost. Efficient memory management. Go's optimized garbage collector is designed for concurrency and low latency, essential for scalable serverless applications. Its efficient memory footprint minimizes resource consumption, further contributing to cost effectiveness in serverless functions where memory allocation impacts pricing. Golang's efficiency provides a tangible advantage. Concurrent programming. Golang's coroutines provide a lightweight and efficient way to handle concurrent operations. This allows Lambda functions to process numerous parallel requests without complexities of traditional threading. This is especially beneficial for applications dealing with high volumes of concurrent events. For instance, in event-driven architectures, Golang concurrency model enables rapid and efficient processing of incoming events. Benchmarking has also shown that due to the efficiency of coroutines, that Golang is able to handle a larger number of concurrent requests than other languages such as Python, given the same memory constraints. In a sense, Golang's performance, efficiency, and concurrency capabilities make it a strong contender for building a cost-effective and highly scalable serverless applications. Now, combining Golang with AWS, that's a powerful serverless synergy. Lambda function support and reduced cold starts. AWS Lambda's native support for Golang allows developers to build highly scalable and cost-effective serverless applications. Golang's compiled nature and small binary size translate to significantly reduced cold start times compared to interpreted languages like Python or Node.js. In real-world benchmarks, Golang Lambda functions often exhibit a cold start durations in tens of milliseconds, minimizing latency and improving user experience, especially for latency-sensitive applications. For example, in a test using AWS Lambda, Golang cold start times were measured to be 10 to 20 milliseconds, while Python cold start times were measured to be 100 to 200 milliseconds when performing the same task. Cost efficiency through optimized footprint. Golang's compiled binary libraries are notably smaller than those of interpreted languages. This results in faster deployment times, reducing the time spent on uploading function packages to S3. Moreover, the reduced binary size translates to lower storage costs on S3. Combined with Golang's optimized execution speed, which minimizes the Lambda runtime, this leads to significant cost savings in serverless environments. Seamless integration and performance. Golang integrates seamlessly with core AWS services like DynamoDB, S3, API Gateway, and CloudWatch. This native compatibility ensures scalability without introducing performance bottlenecks. Golang concurrency model and low latency execution are particularly beneficial when interacting with these services, enabling efficient data processing and real-time event handling. For instance, a Golang Lambda function triggered by an S3 event can process and store data in DynamoDB with minimal overhead and high throughput. Benchmarking has also shown that Golang Lambda functions can achieve significantly higher throughput when interacting with DynamoDB compared to Python or Node.js functions due to its efficiency of Golang concurrency model and native integration with AWS SDK. Now, let's talk about why Golang and Golang with other versus other languages, so performance and efficiency showdown. Overall performance. Golang consistently outperforms Java, Python, Node.js in AWS Lambda environments. This is primarily due to its compiled nature, resulting in faster execution speeds and significantly reduced cold start times. Benchmarks frequently demonstrate that Golang functions can achieve execution times several times faster than their counterparts in repeated languages. This translates to lower latency, improved user experience, and reduced cost in serverless applications. Java. Java offers robustness and rich ecosystem, but it suffers from a longer, colder start times, and in serverless environment especially. The JVM initialization overhead introduces significant latency, especially for infrequently invoked functions. This increased latency directly impact costs due to longer execution times and can lead to poor user experiences in latency sensitive applications. Node.js. Node.js is a popular for serverless due to its JavaScript familiarity and event-driven architecture. However, it underperforms Golang in CPU-intensive tasks and concurrent processing. Its single-threaded nature can become a bottleneck when handling numerous parallel requests, leading to increased latency and potential performance degradation. Benchmarks indicate that Golang can handle significantly more concurrent requests than Node.js under the same memory constraints, particularly in the scenarios involving heavy computation or input-output operations. Python. Python is excellent for rapid development and offers a vast library ecosystem, making it a popular choice for serverless. However, Golang's compiled nature delivers faster execution and lower resource consumption, enhancing the production scalability in high throughput and or low latency critical applications, where performance advantage becomes more crucial. While Python excels in the use of development and speed, Golang's efficiency in terms of memory usage and execution times makes it more suitable choice for production environments, where scalability and cost effectiveness are paramount. When compared to Golang, Python often consumes more memory and has higher execution times for the same task, especially when dealing with large data sets or complex algorithms. By incorporating these data points and contextual insights, the comparison between Golang and other languages become more compelling and informative, highlighting the specific advantage of Golang in serverless architectures. Now, why migrate to serverless architecture? We've seen cost reductions up to 80%. Serverless pay for execution model is a game changer. Unlike traditional servers that incur costs when even idle, serverless charges only for the compute time consumed. This is particularly beneficial for applications with fluctuating workloads or those experiencing infrequent usage. The 80% suggests that it is a significant potential for cost savings, but the actual percentage will vary depending on the specific application and usage patterns. This cost reduction allows companies to invest in more resources into development and innovation rather than infrastructure maintenance. Faster deployment up to 70%. Serverless architectures enable faster deployment cycles through streamlined pipelines. Developers can deploy individual functions or microservices independently, reducing the risk of impacting the entire application. The 70% improvement indicates a notable improvement in the deployment speed, which is crucial for staying competitive in today's fast-paced market. This agility allows for rapid iteration and faster time to market features and updates. Improved scalability up to 60%. Platforms automatically scale resources based on demand, eliminating the need for manual provisioning or capacity planning. This ensures that the applications can handle sudden traffic spikes without the performance degradation. The 60% highlights are the significant benefits of the serverless, enabling applications to handle unpredictable loads with ease. This auto-scaling capability ensures a consistent user experience even during peak usage periods. Operational gains of over 50%. Serverless platforms handle infrastructure management, including the server maintenance, patching, and scaling. This frees up development teams to focus more on building and improving applications rather than managing the infrastructure. This represents the reduction in operational overhead, allowing the development teams to concentrate on innovation and core business objectives. This reduction in maintenance allows for quicker updates and less downtime. Now, let's take a look at the core AWS serverless technologies like AWS Lambda. Lambda is the compute engine of serverless. It allows us to run the code without provisioning or managing servers. Lambda functions are triggered by events from other AWS services or external sources, such as API Gateway, S3, DynamoDB, CloudWatch. So there are a large number of benefits. It is not managed by servers. It frees up developers from infrastructure tasks. Automatic scaling scales automatically based on demand. Pay per execution model. You're charged only for the compute time that we consume. Cost effective, ideal for an event-driven and intermittent workloads. Now, DynamoDB is a fully managed NoSQL database, and it provides a consistent single-digit millisecond latency at any scale. It automatically scales to handle virtually unlimited data and traffic. Supports both document and key value data models. It offers built-in fault tolerance and high availability. It is ideal for applications requiring high throughput, low latency, and flexible data models. Now, let's take a look at API Gateway. The core function of it is it acts as a front door of applications to access backend services, including Lambda functions and DynamoDB. The key features of API Gateway are API management. It simplifies the creation and publishing, maintenance, monitoring, and security of APIs. Protocol support. It supports RESTful and WebSocket APIs. It provides both built-in authorization, authentication, and API key management. Traffic management. It offers throttling, caching, and request transformation capabilities. The use cases are it enables building scalable and secure APIs for web, mobile, and IoT applications. Now, let's take a look at enhancing operational efficiency with AWS S3 and CloudWatch. When we dive deep into AWS S3, S3 is a centralized storage. Like S3 acts as a central repository for various types of data, including application data, backups, logs, images, everything. This simplifies data management and ensures data consistency. Its cost effectiveness. S3 is a pay-as-you-go pricing model, which makes it a very cost-effective solution for large storage volumes of data, especially for applications with fluctuating storage needs. Its integration with Lambdas. Seamless integration with AWS Lambda enables developers to perform data operations directly from their Lambda functions without managing underlying infrastructure. For example, Lambda functions can be triggered by S3 events such as file uploads or deletions. The extreme durability of S3, 99.99999999, it's a lot of 99.99s, ensures the data is protected against data loss, making it suitable for critical applications. Now, AWS CloudWatch is mainly used for logging, metric collection, and observability. CloudWatch provides real-time monitoring and insights into the performance of serverless applications. This allows developers to identify and resolve issues quickly. Log and metric collection. CloudWatch collects logs and metrics from various AWS services, including AWS Lambda, DynamoDB, and EC2. This provides a comprehensive view of the application's health and performance. Customizable dashboards. CloudWatch dashboards enable developers to create custom visualizations of their application metrics. This helps in identifying trends, detecting anomalies, and optimizing performance. Proactive monitoring. CloudWatch allows you to set up alarms and notifications to alert you for potential issues before they impacted users. Now let's talk about the migration strategy, decomposition of it. Identifying these risk boundaries. Domain-driven design. This step emphasizes the importance of understanding the business domain and identifying the logical boundaries between two different parts of the application. The domain-driven design helps in creating a clear map of the business and aligning them with minimal service boundaries. Minimal coupling, starting with the components that have minimal dependencies on other parts of the system, allows for easier extraction and reduce the risks of unintended consequences during the migration. Prioritization. This step highlights the need for strategic planning and prioritizing components for migration based on the complexity and impact. Now, the second step is extracting the microservices, which mainly includes refactoring. This step involves breaking down monolithic applications into smaller, independent microservices. Each microservice should have its own dedicated data store to ensure data isolation and independence. API gateway. Using API gateway to create versioned APIs for inter-service communications provides a standardized and controlled way for microservices to interact with each other. This also enables you easier versioning and management of APIs. Independent deployment. Microservices can be deployed independently, allowing for faster development and deployment cycles. Now, the third step is implementing serverless functions. Lambda functions. This step involves in converting the extracted microservices into Lambda functions. Each Lambda function should be designed with a single responsibility, aligning with a specific business operation. Triggers and optimization. Lambda function should be triggered by appropriate events using API gateway events, S3 events, time motive events, even Cloud Bridge event. Optimizing execution by minimizing dependencies and reducing execution time is crucial for cost effectiveness. Adhering to the single responsibility principles ensures that each Lambda function is focused and manageable. Now, when we move to transitioning the traffic gradually, we can use a triangular pattern. This pattern involves gradually replacing the functionality in the monolithic application with new microservice or Lambda functions. We could use the concept of feature flags, which allows enabling or disabling new functionality without deploying new code. This provides control over the rollout process and allows for easy rollbacks. Canary deployments. Canary deployments involve in routing a small percentage of traffic to the new serverless components. This allows for testing in a production-like environment and identifying any issues before a full rollout. Monitoring and metrics. Closely monitoring metrics during the transition is essential for detecting issues and ensuring a smooth migration. Quick rollbacks should be enabled if necessary. Now let's dive into the event-driven architecture. So this involves event production. Events are generated when a service or component experiences a state change. This could be anything from user interaction to a database update. Services publish these events to an event bus or a message queue. This decouples the event producer from the event consumer. Event processing. Asynchronous processing. Lambda functions are triggered by the events and process them asynchronously. This means that event producer doesn't have to wait for the event to be processed. Lambda functions are ideal for event-driven architectures because they are stateless and can scale automatically based on the demand. State transformations. Updating system state. Based on the data or in the event, system state is updated. This could involve updating databases, caching systems, or other services. Data consistency. Ensuring the data consistency across different services is crucial in event-driven architectures. Now, the fourth step is cascading events. Triggering new events. This state change result from event processing can trigger new events, creating a chain reaction. This allows for complex workflows and business process to be implemented. Managing the flow of events and ensuring they are processed in the correct order is essential for maintaining the system integrity. Event-driven architecture reduces service coupling in general, enabling independent scaling and autonomous deployment. This approach aligns perfectly with Lambda's stateless execution model and pay-per-use pricing. Now, let's take a look at the database migration considerations. So, MySQL or PostgreSQL to Aurora Serverless. Aurora Serverless offers auto-scaling capabilities and is compatible with MySQL and PostgreSQL. making it relatively straightforward migration path for these databases, suitable for applications that require relational database functionality with automatic scaling. Oracle, PL SQL, or SQL Server to DynamoDB in combination with Aurora SQL. This migration path offers cost saving and improved performance. DynamoDB is used for high throughput, low latency data access, while Aurora can be used for more complex relational queries. Ideal for applications that require high performance and cost optimization but may require a hybrid approach. MongoDB to DocumentDB or DynamoDB. So, DocumentDB and DynamoDB offer managed services and scalability by simplifying the database management and allowing for autoscale. So these are suitable for applications that require NoSQL database with high scalability and minimal operational overhead. Memcached, Redis or Memcached to Elasticache or DAX. Elasticache and DAX provide a caching layer, reducing the latency and improving the performance, ideal for applications that require fast data access and caching capabilities. Database migration is the most crucial challenge in serverless transitions. When converting monolithic databases to serverless architectures, organizations must analyze data access patterns and usage requirements. DynamoDB offers high throughput and low latency performance but requires shifting from relational schemas to an access pattern driven approach. Let's take a look at the hybrid deployment models. So we identified the services, we have decoupled them, and we have written the new services in AWS. Now, how to perform the deployment model? Now, if you take a look at the serverless functions, Lambdas, they are ideal for even stateless and highly scalable workloads. They reduce the operational overhead, enabling us to do automatic scaling and pay-per execution pricing. We could use services such as container services in AWS, which are ECS, Elastic Container Service, and EKS, Elastic Kubernetes Service. These services are suitable for stateful, complex microservices that require containerization and orchestration. These provides benefits of portability, scalability, and efficient resource utilization. You could also use managed services like RDS, Elasticache, OpenSearch, etc. So these are designed for specific data needs such as relational databases, caching, and search functionalities. The benefits of it are simplified management, high availability, and performance optimization. Traditional infrastructure like EC2 necessary for resource-intensive or legacy workloads that cannot be easily migrated to other models. We could still use EC2 to achieve them. These offer benefits such as flexibility and control over the underlying infrastructure. So effective migration strategies in general combines components with containers and traditional infrastructure to optimize each service based on specific requirement rather than forcing a single architectural pattern across all the components. Specialized workloads with unique needs they require, such as the long-running process, GPU acceleration, memory-intensive operations, or legacy components can still remain on EC2, while new features like leveraging serverless technologies can move to AWS. This incremental approach delivers immediate benefits while maintaining the system stability throughout the migration. Now, let's talk about the DevOps integration and the continuous improvement and continuous deployment. So, infrastructure as a code, Terraform or AWS Cloud Formations are highlighted as the tools for codifying infrastructure. These ensures the consistent and repeatable deployments. They also offer version control of infrastructure, allowing for tracking changes and rollbacks. These facilitate collaboration among team members throughout the code reviews and shared infrastructure definitions, automates the infrastructure provisioning and management. Now, continuous integration to AWS code build and GitHub actions are mentioned as tools for automated testing. Unit tests, integration tests, and infrastructure validation are emphasized as essential components for continuous integration. They offer a variety of benefits such as early issue detection, improved code quality, faster code feedback. Now let's take a look at deployment automation. So AWS Code Pipeline is highlighted as a tool for orchestrating serverless and serverless deployments. And basically, you could use any other internal tools. Most of the tools should be compatible with AWS in general. Deployment strategies, canary releases, and blue-green deployments are mentioned as strategies for reducing risk and maintaining availability. Automated deployments automates the deployment process and by reducing manual effort and errors. Canary releases, blue-green deployments minimize the impact of the deployment failures. Monitoring and CloudWatch, X-rays, and specialized tools are recommended for monitoring and observability. So logging, distributed tracing, and alerting are emphasized as crucial for detecting and resolving issues. These offer benefits such as real-time insights, proactive issue detection, enabling proactive detection and resolution of issues before they impact users. And they also offer the benefit of improved troubleshooting, simplifies the troubleshooting through logging and distributed tracing. When we talk about how do we overcome these migration challenges, there are some highlighted issues which we usually see with migrations, such as cold start latency. Cold start occur when a Lambda function is invoked for the first time after a period of inactivity, leading to increased latency. A couple of solutions are provision concurrency, pre-warms Lambda functions to reduce cold start times, scheduled warming, regularly invoking the Lambda functions to keep them active, code optimization, reduce function size and dependence to minimize initialization time. Lightweight runtimes in Java and .NET uses optimized runtimes to reduce the initialization overhead. Distributed system complexity. Serverless architecture often involved in a distributed systems where it can be complex to manage and troubleshoot. A couple of ways to overcome this is comprehensive observability by using the X-ray and CloudWatch provides end-to-end tracing and monitoring for distributed systems. Eventual consistency, design systems to handle eventual consistency rather than relying on strong consistency. Using circuit breakers, preventing cascading failures by isolating failing components, and using back-off strategies, implementing retry mechanisms with exponential backoffs to handle transition errors. Legacy code refactor. This is the third step. Challenge. The challenge that what we see is migrating the legacy code to serverless can be challenging due to highly coupled dependencies and monolithic architectures. A couple of ways to overcome these: incremental refactoring breaks down the monolithic application into smaller independent components, identifying boundaries and isolating dependencies, identifying the logical boundaries and isolated dependencies to facilitate refactoring. We could use something called a Strangler pattern, gradually replacing the monolithic functions with serverless equivalents while maintaining the system stability. Now, the last and the most important point is the security considerations. So, serverless architectures require careful security considerations, including access control and vulnerability management. A couple of solutions to handle security would be implementing function level IAM permissions, implementing the least privilege principles by granting only necessary permissions to Lambda functions. AWS Security Hub, and you could use other services like AWS Security Hub, Amazon Spectre, and serverless security scanners to identify vulnerabilities even before deployment. Right. So in the next, let's take a look at a case study of an e-commerce platform migration. So during the initial assessment, the platform experienced significant performance degradation during peak seasons, with the transaction processing slowing down by 400%. While performing an analysis, the bottlenecks were identified in the monolithic architecture, leading to prioritization of inventory and payment systems for migration. One of the key insights that was outcomed is the phase insights, this phase, like basically initial assessment phase insights, the importance of going through a thorough analysis and prioritization before even embarking on a migration. Database transition. The product catalog was migrated from MySQL to DynamoDB, a NoSQL database without optimized access patterns. For this, a dual write approach was used to ensure zero downtime migration and maintain data consistency across system. So this database transition phase demonstrates the importance of choosing the right database technology and implementing a robust migration strategy. So next comes the first migration phase. The payment processing system, which was extracted into Lambda functions with API gateway using an event-driven architecture. This resulted in 30% reduction in infrastructure cost and a 50% improvement in the response time during peak traffic. The key insights of this phase, it highlights the tangible benefits of migrating critical component to serverless. The fourth point is like the complete serverless architecture. The complete serverless implementation achieved an 80% cost reduction in normal operations and enabled the platform to handle 10 times the traffic surges without performance issues. The development cycles improved from monthly releases to multiple daily deployments. This key phase demonstrates the transformative impact of a complete serverless migration on performance, cost, and development agility. Now, we could take a look at the roadmap for successful serverless migration. The key would be assess and plan, analyzing the existing architecture to identify suitable candidates for migration. Then mapping dependencies between services to understand the impact of migration. Prioritizing migration candidates based on business value and risk. This is to create a clear understanding of the current state and develop migration strategy. During the initial pilot, implement a POC with a non-critical isolated service, expertise, build internal expertise in serverless technologies, establish architectural patterns for serverless development. The whole goal of this initial pilot is to validate migration approach and build confidence. Expand and refine. Gradually scale a migration to critical workloads. Refine the architectural patterns based on experience and feedback. The goal of this expanding and refining is to ensure a smooth transition of core business services to serverless. Enterprise transformation. Adopt serverless as a standard for development. Embrace a cloud native culture, restructuring teams around business domains rather than technology silos. The goal of this enterprise transformation is to fully leverage the benefits of serverless transform the organization. So overall, if we consolidate these into two couple of points, is begin with the thorough assessment by mapping the dependencies and prioritizing migration candidates based on business value and risk. Launch a pilot with a bounded non-critical service to build expertise and establish architectural patterns. Methodically expand to core business services while refining implementation patterns. Finally, transform your organization by adopting serverless as a standard for new development and restructuring teams around business domains rather than technology silos. In conclusion, we have explored the significant advantages of migrating a serverless architecture on AWS, from cost reduction and improved scalability to enhanced developer agility. The benefits are very clear. Remember, this journey is more about just technology. It's about transforming how we build and deliver applications. By embracing serverless, we are positioning ourselves to innovate faster, respond to market changes more effectively, and ultimately provide greater value to our users. The future of cloud computing is serverless, and I encourage you to explore how it can empower your organization. Thank you all. Thank you so much.